Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And he's going to give us a talk on something that has to do with economic game theory, yes?
Right.
Okay, good.
Okay, I think this was supposed to be a trivia question, an auction-related trivia question. The point was to see if anyone who didn't know about this before, from in advance, could figure out what this was.
So I didn't know. So I said,
Christian!
Okay, so I'm going to talk about trade-offs.
to answer that question?
Eventually. But I'm interested to see if anyone who didn't know about it could actually deduce it.
Yeah, how could someone not know
Oh,
that?
okay, that's
and on
good.
what basis would they deduce it? Just from the cost? Or?
No, there's hair and there's the cost. Yeah, that's right.
So
Yeah,
of somebody famous.
it has to be someone famous, and the kind of, and it has to be someone dysfunctional also.
Yeah.
Okay.
He doesn't like, he watches TV, but he doesn't watch the news or surf the web news.
Yeah.
He doesn't know.
No, it's part of pop culture now. So I'm going to talk about trade-offs.
It's just normal hair after all.
Yes.
It's normal.
That.
That is available on eBay though. The question is which one is fake and which one are real.
That's right. That is also true.
You're going to get a DNA.
No, they withdrew it from the auction. I think she paid for it, and then that's the story.
She bought her own.
No, she bought her own hair back.
Right, that's what
Is it considered body part because that's illegal
Oh, I see.
on eBay?
I see.
to sell body parts.
No, no, but fingernails, unless ripped out, and hair is sort of
On that. Okay.
Okay. So I'm going to talk about trade-offs in a certain auction setting. So this is joint work with my advisor Tim Rafkarden, and also Shuchi Chawla and Arnak Mehta. So I'll spend the first few slides describing the auction setting. So these are auctions with cost, and by that I mean that when the auctioneer services people, the auctioneer incurs some amount of cost. So here's the setting. So you have a universe U of k bidders, each with a private valuation Vi for service. And it's a binary thing. The bidder either gets serviced or not. The auctioneer picks a subset of the bidders to service, and any subset of bidders can win. But the auctioneer incurs some cost depending upon which subset he decides to service, or she. So you can look at this as either auctions with cost or alternatively as resource allocation with certain incentive issues. And I'll explain with an example about allocating multicast. And this is a problem that has been studied by Feigenbaum et al. And also Jain and Vasarani. So here is the problem. So here's what a multicast auction looks like. So you have an edge-weighted graph with a designated node, which is a root, and it's an undirected graph. And the players have some valuation for being connected to the root. And the way the auction works is that it collects the bids and decides which subset of players to service. And then it finds an approximate Steiner tree on the terminal pairs which it selected and the root. And it builds this tree, and then naturally when it builds this tree, it incurs some cost. So that defines the cost. And now it's going to charge prices to these players.
So in your picture, which ones are the Steiner vertices?
So in my picture, the root is definitely one of the terminal vertices. So I don't know which way the definition goes, but the root is a required vertex, and some subset of the players will be selected. Okay, so these colorful disks are players. So some subset of these will be selected. And a Steiner tree is built with a required vertex set being the selected players and the designated node, which is the root.
I see. Your example just doesn't have to have standard vertices.
So that's right. So in some sense, yeah, I guess I should have drawn one, green circle here or something. So I guess we could study revenue maximization in this setting, but what we choose to study is this notion of efficiency maximization.
Oh, do you incur? So is the cost just proportional to the? Is it just a function of the vertices who are eventually served, or also a function of the intermediate standard vertices?
So the cost is defined as, so when we select certain required vertices, we construct a tree which includes those vertices and the root. The cost is the cost of this tree, which is defined by the cost of the edges in the underlying graph. So these are the auction objectives. The auction objectives are, so we have two constraints. The constraints are that the bidders should not have an incentive to lie. So the bidders are going to get allocated service and also going to pay some amount. And we want to conduct the auction in a way that is robust to manipulation. So we want the bidders not to have any incentive to lie about their valuations. Also, we'd like budget balance, which means that the auctioneer incurs some cost in servicing the bidders, and we'd like for him to recover this cost. And the third, the main objective, so these are constraints, and the main objective is efficiency maximization, which is he wants to select a set of bidders such that the total value, the difference between the total value in this set and the cost incurred is maximized. So that's called surplus for obvious reasons. Right, so you have these three objectives, and what we'd ideally like is something which gets you all these objectives. But it turns out that there are fairly strong impossibility results which tell you that you can't get all these objectives at the same time. So it's also true that you can get any two of these, almost. So for instance, if you didn't want truthfulness, and if people were willing to tell you the truth anyway, then maximizing surplus is a problem. Ignoring algorithmic issues, you can always solve this. And then you just charge prices in some way so that you recover the cost. But it turns out that the fact that you require all three objectives is what makes this problem hard. And a natural reaction to this impossibility result is to look at approximation. So the first thing you could ask is that what if you approximated only the cost recovery? So if you said that, we don't need the auctioneer to recover all the cost, but he'll be happy if he recovers, say, at least half the cost at all, every time, but manages to optimize efficiency and get truthfulness. Turns out that this is also not possible, and this is again due to these hardness results. So what we're going to look at is a family of mechanisms which gives you truthfulness and budget balance. And then we ask what approximation of efficiency or surplus we can get. So that's the problem.
For completeness, even approximate efficiency is not possible if you want budget balance time.
Yeah. So in fact, I was coming to that. I was trying to sort of motivate our definition and clarify that point also. So we are going to talk about a family of mechanisms that are truthful and budget balanced. That is, they always recover all the cost that they incur, and they're truthful. And they're called Moulin mechanisms because they were studied by Hervé Moulin, and they're based on what is known as cost sharing. So I'm describing Moulin mechanisms. So Moulin mechanisms are based on cost sharing. So first let me describe what a cost sharing method is. So a cost sharing method does the following. For every possible subset of the players of the universe, given that the mechanism incurs some cost, a cost sharing method prescribes a way of partitioning this cost among the players so that it can be recovered. Right? So here's an example. So this is a very simple instance of the problem that I stated earlier. So you have a root, and you have a number of players sitting at the other end of this edge. And recall that the players get value from being connected to the root. And serving any non-empty subset of these players has cost 1. Right? And the way a very simple cost sharing method is this cost sharing method called split. What it does is that given that any subset of the players needs to be served, it splits this cost evenly among those players. Right? So that's what a cost sharing method does. This is an example of a very simple cost sharing method. So now I'm going to tell you how Mullen mechanisms work. So here's how they work. You collect bids from the players. So there's one number that you collect from each player. And you start off by saying that the mechanism starts off by saying that let me try and service all the players. So S is equal to U initially. Now what it does is that it invokes the cost sharing method, okay, to get suggested prices for that set. If all the players are willing to pay these prices, then it stops. If not, it drops one of the players which was not willing to pay its bid, which was not willing to pay its charge, and then it continues. And by continuing, I mean that it reinvokes the cost sharing method on the remaining subset of players.
But you don't have to have something as simple as split to do this.
No.
You need monotonicity.
Yes.
That's right. So that's my next slide. You're getting ahead.
So what is the definition of chi? Could you please?
So chi is a cost sharing method. What it does is that for every
specific one that you haven't specified.
No, I haven't. So I'm about to give you an example with a specific cost sharing method.
Split, but it could be something else.
Yeah, I was trying to just define it generally because later we're going to look at multiple cost sharing methods.
Do you drop a player or all players?
So you drop a player, which can't. So it turns out that you can drop all the players which don't pay their values, but it's for a very specific reason. For now, let's assume that you drop an arbitrary player who can't pay its charge.
So if you drop different players, it may result in a different.
I'll clarify on the next slide. It'll be clear. So let me give you an example of how the Mullen mechanism works with split as the cost sharing method and this very simple cost function. So those are the bids. Now recall that what split is going to do, so the mechanism starts off by trying to service all the players. Right? So recall that the way split works is that it distributes the charges evenly. So each player is going to get offered a price 1/5. I should have had this. Yeah, that's fine. That's fine. Yeah. So, yeah. So what's going to happen is that in the first iteration, player number 4 is going to be deleted because he can't pay his cost share. And then in the next iteration, player number 1 will be deleted because it can't pay its current cost share. But at this stage, you can see that all the bidders are willing to pay their respective cost shares, and so the mechanism stops. In particular, it services players 2, 3, and 5, and it charges them 1/3 each. It's easy to see why this mechanism is budget balanced. The budget balance simply follows from the definition of the cost sharing method. It's an invariant throughout this process.
So would the airlines do better if they did that instead of for the car?
Say that again?
Would the airlines do better if they did that mechanism instead of for the car?
But they want to
They
earn
want to
money.
do it over time, not at one point in time.
So, no, say that again? I
think we can go on.
okay, that was, I see. Okay, so the mechanism is budget balanced, obviously. And it turns out that if the cost sharing method satisfies a certain property called cross monotonicity, then the mechanism is truthful. Essentially, this is the monotonicity that he was talking about. So what you need is that, suppose you look at the cost share of a particular player in a particular set, then cross monotonicity says that as the set shrinks, the cost share of a player can only go up. So it turns out that what Mullen proves in his paper is that if chi is cross monotone, then the Mullen mechanism, which behaves like the way mentioned on the previous slide, is in fact truthful. So here is our goal. Our goal is to identify optimal Mullen mechanisms. Like someone pointed out, we could have different cost-sharing methods. And what we'd like to now know is that, which is the best cost-sharing method.
Best in terms of, yeah.
So best in terms of the third thing that we required. So this is giving you two things already, truthfulness and budget balance. And best in terms of efficiency or surplus maximization. And we already know that, because of the impossibility results, we're going to look at approximation.
Wait, can you go?
Yeah.
So in your example, why is it sort of truthful? Because
Oh, right. Split is cross-monotonic because, so the cost-sharing method split is cross-monotone because as the set shrinks, the amount of charge to each player goes up. I should have.
But so it's budget balance in the sense that the costs are exactly
Equal to exactly.
because there's no profit in particular. So you want in addition now make profit.
So no, we are not looking at revenue at all.
Efficient social welfare is.
So yeah.
So how you define social welfare?
So
In terms of the valuations.
So social welfare is the total value served minus the cost incurred. So now in this example, the total value served is 4 plus 2 plus 1 and minus 1, so it's going to be 6, the social welfare.
And now you want to maximize all of these.
Right.
Right.
Approximately.
Because of these impossibility results, we're going to try and approximate this. Right. So subject to these constraints, truthfulness and budget balance, we are trying to see how well you can do on social welfare approximation. So to clarify, so first of all, I guess one question is why, what specific cost sharing method works best? But the second question to ask is, why do things this way? Why not do something totally else? So the answer is that it turns out that this is the only general way we have that we know of right now.
Oh, okay, so that's not a theorem, that first bullet.
No, that first bullet is not a theorem.
Okay.
The second one is.
Yeah, I know. So I was wondering what way you were made. So only currently known general method, but
That's right.
no impossibility results for.
No. So the only result which sort of gets close to something like that is one which says that if you wanted a stronger notion of truthfulness and you wanted budget balance, then Mullen mechanisms are pretty much the only method.
So it's group strategy proof in the sense that all but one player can collaborate. It's still strategy proof.
So actually, the definition of group strategy proofness is that players can coordinate their bids. So it's robust against players coordinating their bids, but players cannot pay each other. So it's an interesting definition. And it's not clear it's the right notion of collusion resistance, but it's interesting and technically it's in fact very. So this is why we are looking at Mullen mechanisms. So here's some bad news. So recall how we defined surplus. It's value served less cost incurred. Okay, and here's a very simple example. So you have k players sitting at this node. This should be green. Okay. And the edge costs 1. And let's say that the players' bids are as follows. So it's 1 over k minus epsilon through to 1 minus epsilon. Epsilon is a small positive number. The optimal solution services everybody. It incurs a total. It accumulates a total value approximately close to the kth harmonic number, and it incurs a penalty of 1 because it incurs some cost in servicing those people. But let's see what the Mullen mechanism does. It's
How big is roughly HK?
log k. But there's going to be something really bad happening.
Yeah.
So the thing is that in the first iteration, the Mullen mechanism, it's using split. It charges everyone 1 over k. The first player doesn't want to pay that. Gets deleted. And in general, in the ith iteration, the ith player will get deleted. And finally, you'll end up with no one.
And we saw the beginning of that in the last one, but then it stopped. I mean, in your little example, we saw.
Yeah, exactly. So this is like, in some sense, a really bad example. And what's the surplus of the Mullen mechanism? It's 0. It incurs no cost because it doesn't serve anybody, but it also doesn't serve anybody, so the valuation served is 0. If you look at this in terms of multiplicative approximation, it's a disaster.
And that's related to net neutrality debate what people were having. If everybody pays the same, then some poor guy will withdraw. Oh, I don't want DSO, and then it become expensive for other. And
Oh, I see. Oh, that's an interesting.
that's it.
Uh-huh.
What was the comment come on?
So you should again read
We were having debate once here, just
With Albert Greenberg.
Yeah, about net neutrality. And one of the things is, if we try to be fair with everybody, then the poor person may find it more expensive, and then he doesn't want DSO. And that increases the cost for other, and then there may be another person who had enough money earlier is relatively poor now.
That's kind of
And so there's some loss of efficiency.
Right, a proof that net neutrality is a disaster in the worst case.
If you have a huge fixed cost like airline or something, you should be doing price differentiation to serve more people.
Right.
Rather than neutral pricing.
Right, so net neutrality is sort of...
Everybody should pay the same.
They want to make it a law that you're not allowed to charge people different amounts.
Based on what you think they can afford, like charging Microsoft more, so of course, the Microsofts of the world don't want it, but also, want net neutrality, and Moby also wants net neutrality. So it seems like different sides of the spectrum want it, but really, if Moby understood, given his values, he should not want net neutrality.
But hopefully, I guess, the values are not this skewed. That's the only saving grace.
Right, in the worst case, it's really terrible.
Yeah, one hopes that. But it turns out that something really bad is true. The example that we saw specific to Mullen mechanisms and the split cost sharing method, we saw disaster essentially.
Who's the et al. There?
It's Sami. It's FKSS. So it's yeah. Yeah.
Okay.
Sami and Krishna. Yeah. So the example that we saw specific to Mullen mechanisms in the split cost sharing method actually is much more generally true. Any truthful mechanism that is approximately budget balanced, even for the very simple cost functions, must yield an arbitrarily bad approximation of surplus. So in some sense, what this is saying is that suppose we are trying to figure out what the right, so suppose we assume these constraints, truthfulness and budget balance, and we are trying to now figure out which cost sharing method is the best. We can't do it this way because you're going to get arbitrarily bad answers for all the cost sharing methods. So here's what we do. Here's our solution. It's actually a very simple transformation, and it allows us to look at, to identify optimal mechanisms under the constraints that we have using multiplicative approximation. So we study efficiency loss rather than studying efficiency. So the way we define the social cost of a set of players to be the cost incurred by servicing those players plus a penalty term which is incurred by the mechanism for not servicing the other people.
So U is your full, U is the full set. Yeah, okay.
U is the
Similar,
universe of...
like price collecting.
Exactly. So in fact,
Price collecting algorithms that you serve some of them and you add the penalty of not serving the others.
So in fact, the same thing happened with price collecting, where, yeah, sorry.
Definition, the social cost would be actually bigger than the maximum surplus you could have achieved. If you, let's say, you serve just nobody,
Yeah.
then your loss is P of U, but
Yeah.
your surplus is never P of U.
Yeah. So it turns out that when we do the worst case analysis, we would prune those players away. So this is actually a technical point. I'll discuss this offline if you're interested.
You should have taken CS plus B U slash S minus C of U slash S. You could have decreased that surplus to make it.
So it turns out that we effectively do that because okay. Let me.
Theorems harder because minus signs in objective function.
Then there is going to be again a problem.
You're saying minus C of U minus S.
Yes, because that's the surplus you could have gotten.
And then you
Yeah,
wouldn't
that might
get
be
something
a very
negative, at least.
So it turns out that in the theorems that we have, S is going to be the null set.
What?
So this is a technical. So in some sense, so you said minus C of U.
So wait, and you serve, S is a null set, your solution is to serve nobody, that seems.
Your solution.
No, I'm doing, so when I'm doing
gonna
worst case
iteratively
analysis in some sense.
Serve.
Let me actually go through a few more slides, and then once we see the theorem statements, let's come back to this. So just to complete price. So in price collecting, you had a similar transformation, which suddenly allowed you to look at things in terms of approximation. So that's a connection. So anyway, this is our new goal now. So our new goal is subject to these constraints, the cost recovery constraint and the truthfulness constraint. Let us try and identify an optimal Mullen mechanism. By that I mean, let's find the cost sharing method which gives us the best worst case approximation of social cost.
I mean, one way to generate constant factor approximation, if you didn't have that before, is just to add a large constant to your objective function.
That's true. So this is a story we heard. There's this systems professor at Stanford who tells this story of how to first do systems work and then justify it. What you do is that to say that your work is good, you just find the right thing to look at. So essentially, you first do the work, and then find out exactly where it improves things, and subtract out the rest, essentially. So, I'll hopefully convince you I'm not doing that. So our contribution is that, so what do we know so far? We know that the budget balance, so Mullen has essentially reduced the problem of designing truthful budget balanced mechanisms to designing cross-monotonic cost sharing methods. So what we are going to do is we're going to essentially show that analyzing the efficiency loss of such mechanisms is also a property of the cost sharing method. So if you just see the cost sharing method, I can tell you what the efficiency loss is, and in a tight way. So it's going to be both lower bounds and upper bounds. So I'm now starting to motivate the definition of this property of the cost sharing method. So we call this property summability. Maybe there's a better word for it, but we are still looking for a nice term. But here's what's happening. So essentially, let me first argue what kind of approximation are we going to get. So let's just look at that for a second. So again, it's the same example. The cost is 1, and these are the valuations. Again, the optimal is the same thing. You serve everybody, right? But now we're looking at social cost. Because we serve everybody, the first term in the definition of social cost is going to be 0 because you didn't exclude anybody, and because you service and incur a cost of 1. What we're going to have is that the optimal has social cost 1. Right? So social cost, we are trying to minimize social cost. So minimization problem. And what will the Mullen mechanism do? It will delete all the players, but you can now quantify how much the efficiency lost is. It's going to be it's okay.
Which you saw anyway last time. Yes.
That's right. So the only change are these two. I'm just using a definition and telling you what it looks like. So now let me try and define summability. It's actually the most natural definition you can think of. What we're trying to do in some sense is to cause as much deleted valuation as possible. So here's the definition. So if you fix a cost sharing, so for a fixed cost sharing method and a particular cost function, the summability is defined by a worst case quantity, and it's the worst case over all possible subsets of the universe and orderings of players within this set. Should have probably said sigma. And it's the ratio of two quantities. It's the ratio of the worst case sum of the cost shares at deletion to the total cost. So in particular, what we saw on the previous slide, so notice that the property that I stated is stated purely in terms of the cost sharing method, right? And this is because essentially to cause that amount of deleted valuation, I simply need to set the values slightly lower than that cost share to cause it to be deleted. Right? And then since we're doing worst case analysis, the rest of it is well motivated.
Go back.
Yeah.
So let me actually
This is I belongs to S.
let me go through this a little bit. I think this needs a little more. So we're looking at the worst case over all possible subsets, and given a subset, the orderings of the elements within the subset. What we're looking at is the cost share of the ith element in the ordering just before it's going to be deleted. That means all the other people before it in the ordering are already gone. So we're looking at that particular set where it's just about to be deleted, and we're looking at the cost share of the ith element at that point.
And this is the thing that each time kind of just managed to chip away. So
Exactly.
there's nothing left.
Exactly.
But the maximum is over.
We also
So
have
why
to
is
worry
the
about the
maximum
order.
attained for that one just before it skips away?
For which one?
Assume that these were exactly the bits.
Yeah. Assume that the bits were slightly less than this.
So think of this last example. What is this doing? This is giving you, oh, I just lost that. That was what I needed. I just lost that. I just lost that. And then
Why does
it
it
chewed
do
everything
that?
up. That sum
That's a
is what
definition.
chewed everything up before.
So what is the sum over?
So the sum is over I.
I in S.
So given yeah.
I and X.
I
Yeah.
in the subset you've chosen.
So yes. So it's the ith element in the ordering over the subset that you've chosen.
So
That should
this
be
was
an
the
I missing.
cost just before
Deletion.
that one got kicked out, then the plus the cost just before the next one got kicked out, plus the cost just before.
Where do I see the before in this?
Just from what he said. Sigma I is the I mean, that's what it stands for. It's the
So it's the ith
ith
element.
one to get kicked out in
Right.
that
Oh, I
ordering.
see.
Right.
Okay.
That's his notation.
Yeah. So I mean it's this quantity.
Some of the diagonals there.
It's a sum? No, it's a.
It's the sum.
It's the sum.
So I selected a particular ordering in my head, and then I set these valuations so that that ordering of deletions was realized.
Okay.
So it's essentially inverting this process, and the definition inverts it. So,
What does it mean for it to be alpha summable?
so
Oh, that.
yeah, so if this number is equal to alpha,
I see.
then we call it alpha summable.
Okay.
Actually, it's this number is bigger.
No, I mean it tight. So I mean it.
Or alpha summable
Yeah,
really
it's
that
tight.
alpha.
It's that
It's
alpha.
not about
Yeah,
S.
yeah.
That's okay.
It's a tight. So I'm just saying it. There's worst case anyway, right? We're doing this max, so we don't need it. So when I say alpha approximate, I mean alpha approximate for the social cost objective. So the first part, the fact that this is that the summability is a lower bound on the approximation of social cost, kind of follows from the examples that I have. But what's more sort of interesting is the upper bound. So what we proved was that if you have a Moorean mechanism based on an alpha summable, beta budget balanced cost sharing method. So beta budget balance means that you recover at least a beta fraction of the cost. Actually a 1 over beta fraction of the cost.
So beta could be 1.
So beta could be 1. So for split, which we just saw, beta was 1, it was perfectly budget balanced. Then the corresponding Moorean mechanism is alpha plus beta approximate for the social cost objective. So this is something we proved. So the point of this is that suppose you have an O1 budget balanced cost sharing method, then the parameter, which is summability, determines completely the approximation factor of the corresponding Moorean mechanism.
Wait, is alpha always larger than 1?
Because the cost function is increasing, something which I didn't say, and the cost shares are cross monotonic, those two together imply that alpha is always larger than 1, along with the fact that the cost shares are budget balanced. So it's a combination of a few things, but that's true.
So typically alpha is log n or something like that.
That's right. It could be worse, but yeah, it's going to be a polylog. So now that we've sort of reduced studying the efficiency properties of a Moorean mechanism to just studying this particular parameter of the cost sharing method, by bounding this particular parameter, the summability, we can sort of say something about the efficiency of the mechanism using the previous theorem. And so we have a number of applications of this theorem. So we looked at various cost functions. So when I'm saying multicast cost sharing there, I mean that the input graph is a tree. And in that case, it turns out that a particular cost sharing method, it's basically split, is optimal. And the optimal approximation factor on social cost is h sub k. What I need to prove here is I just need to say that the summability is h sub k. Since the budget balance is constant, I can sort of say this. The second thing is for facility location. So in facility location, the problem is that you have facilities and you have cities, and cities are trying to connect to facilities. And we assume that cities have valuations for being connected to any facility. And there, it turns out that you need a different cost sharing method. And we sort of, this is by Martin, Pal, and Eva Tadas. And it turns out that we have some results there. The third one is interesting. It says that the Jain Vajrani cost sharing method is optimal, and the optimal approximation factor is theta log square k. Now, to clarify, in this case, I sort of mean that the graph, it's an input graph, and it's a general graph. It's not a tree, and you can sort of see that because it's not a tree, this is log k, and so you're getting this extra squared term. And this is kind of interesting because
Go up. So the multicast cost sharing you say extends to all submodular cost functions. I mean, multicast is budget balanced, but it's not submodular.
so on a tree it is submodular. I'll come to it. I have slides. Let me just come to it. So the interesting thing here is that it turned out that these mechanisms were designed without efficiency in mind. But somehow there's some underlying notion of fairness in these mechanisms which causes them to be optimal. So there's something strange going on there. But I also have an example of a case where there was a mechanism designed before we proposed this notion. And after we proposed this notion, some people went and improved the social cost approximation. So there have been these are actually applications of our framework by other people.
So I have a question. I mean, before you didn't have a sort of turn a little bit to my question before. Before you had a cost function which was not a constant factor. But there's no way to introduce a function of z cost function that this reduces to z.
Oh, this reduces to...
Well, I mean, the way I see it, you sort of redefine what sort of
notion of
optimum is,
right?
By sort of going now...
Well, by adding that extra
Right.
By adding this extra tag.
Right.
Is there some way of formalizing that it's really something new and not something trivial in the sense that you couldn't just introduce a transformation, a simple mathematical transformation of your old cost function to achieve this result?
Let me give you an example. So again, let's take the single edge cost function. And you have two cost sharing methods. So the first one is split. And the second one is serial. So serial, let me define the cost sharing method serial. The cost sharing method serial works as follows. It considers a fixed ordering of the players. And what it does is that it asks players in that ordering whether they're willing to pay the whole cost. So it asks the first player, are you willing to pay the whole cost? First player says no. That player gets deleted. And then the second player is asked. But if any player says that he's willing to pay the cost of 1, then all the players after that player are serviced for free. Okay, so two cost sharing methods. So it turns out that suppose you look at the approximation of social welfare for these cost sharing methods, the answer that you will get for both is 0. Whereas if you look at social cost, you would get log k and k. Okay, so in some sense, if you look at the old notion of approximation, it wouldn't give you any information. Let's see what happens here. Suppose all the players had, so the cost is 1. Suppose the players had valuation 1 minus epsilon evenly. What would happen is that, we would ask the first player whether he's willing to pay 1, gets deleted. We ask the next player and so on. So all these players get deleted. The amount of lost valuation will be proportional to k. So in some sense, what we are saying is that, so also just to clarify, both split and serial are budget balanced, and they're both truthful.
Now, split seems to be more adapted if all players are equally rich or sort of value things equally well, whereas this other one might be better if I know that there's some rich people around whom I can milk.
That's absolutely right. So this is so some of this is an artifact of the fact that we are looking at doing worst case analysis.
No, but maybe.
So if you had some priors.
The case for split would be.
He showed you the worst case.
You have a
He
theorem
showed
which
us
says that
the
log
worst
k is the
case
worst
versus
case for
worst,
split.
yeah.
Oh, I need to say something more.
But there may be a best case for the worst case.
Because of worst case. That's.
There could be sort of a best case for. Will you talk? You mentioned at lunch some things where I have some notion about.
I have a slide on that. Let me come there. So I essentially just a few slides back showed you a lower bound of h sub k for split on the summability. Let me just tell you a little bit of why the upper bound is true. And if we upper bound the summability of split by h sub k, then essentially using the theorem that we had, the lower bound and the upper bound are very close. So it's going to be. So let me define split cost share slightly more generally for trees. So the situation is you have a root and you have an input tree and there are players sitting on various nodes. And now the thing is that we are trying to see how the cost sharing method behaves. So to remind you, the cost sharing method given a set S figures out how to partition the cost to the particular and assign it to the particular players, right? So in this case, suppose we were trying to service these players, then what cost would we incur? Essentially, there is a minimal subtree which includes all the players that you want to serve. And in this case, it's all the black edges. So that the sum of those edges is going to define the cost. Right. And to define split generally, here's what we do. Each node has a unique path up to the root. Right? And then the paths of different nodes intersect along these edges. So for instance, this edge is being used by this player, this player, this player, and this player. So what we'll do is we'll split the cost of this edge equally among those 4 players. So it's a natural generalization of the single edge example. Right? So for instance, the cost share of this player is given by this expression. So for each edge, we prescribe how much cost that player incurs, and you add it up and you get a cost share. Right? Just to clarify, the cost function, the tree cost function is submodular, because what's happening is that suppose you look at the incremental cost of adding a player to a particular set, this diminishes as the set grows. That's just. So it turns out that these split cost shares, it's very easy to bound the summability of this cost sharing method because these split cost shares satisfy a property called order independence. So in particular, whatever ordering sigma we choose, it will result in the same summability. Why is this? Because in some sense, each edge contributes some amount to these cost shares, and transitively contributes some amount to this whole sum. In whatever sequence we delete the nodes, the amount that an edge contributes to this particular quantity is the same. So I'm arguing this for a fixed set S. But I'm arguing that different orderings will result in the same summability.
Well, there's only one path for any given die, so that's kind of, doesn't it?
Right. There's
Yeah.
It's very
If there were
simple.
2 different paths, then you might have gotten 2 different things if things got deleted on
Exactly.
this path or that
Exactly.
path, since there's
So there's a consistency property which sort of gives you this. Yeah. So it turns out that suppose I was trying to upper bound the summability of split, there's a very simple argument which works. So we already know that any ordering is going to give you the same summability. So what we do is you pick a random ordering. And let the random variable xl denote the value of the lth term in this summation. So what you can show is that conditioning on a particular set SL occurring, the value of the random variable is going to be the cost of that set divided by L, the number of players in the set. So this is because of budget balance. So you have a particular set, and since you're picking a random ordering, any one of the players could be deleted. So any one of those cost shares could be involved. That's why you get this. And because the cost function is non-decreasing, you get this inequality. You add it up, and that's what you prove. So that's how you get the upper bound. So again, to clarify the upper bound, so the upper bound and the lower bound match. And it turns out that there's something very interesting, which is that the split cost sharing method actually falls out of a more general definition of the Shapley value. And for those of you who know the Shapley value, it turns out that one of the characterizations of the Shapley value is that it's actually characterized by this order independent summability.
Who's that, John?
This is Hart and Mascolel, so two economists.
Hard is the hard.
So the thing is that
Is that Hart?
Sergio.
Sergio.
Oh, he was here
Yeah.
last week.
Oh, I see. I'd have liked to meet him. Okay. So I mean, it turns out that the way that computer scientists prove a problem NP complete when they have nothing else to do, and if they're feeling really bad about their research, they find a new problem and prove it hard. The standard task for economists is to prove a new axiomatization of the Shapley value, in some sense. So one of these, one of these adventures into proving a new axiomatization actually gave us this. It turns out that they were not doing anything related to efficiency at all, but they sort of proved a new axiomatization. But the bad thing, the sad thing is that it turns out that the Shapley value is not always cross-monotonic. So if you recall, for Mullen mechanisms to be truthful, we wanted the cost-sharing method to be cross-monotonic. So because the Shapley value is not cross-monotone for most combinatorial cost functions, we actually need to design new cost-sharing methods for things like the standard tree problem, the facility location problem, and so on. It also turns out that you need to also sacrifice some amount of budget balance. It's even impossible to just get budget balance and cross-monotonicity. So this is work done by people sitting here. There's 2 people sitting here. Third person's gone. So okay. And it also turns out that because of this,
Well, she's actually more Iranian than she was.
Honorary Iranian.
What?
Honorary Iranian.
Yeah.
Honor-
She-
so it turns out that because
We're connected to Iranian.
Now you make sexist.
oh my God.
Just a fact sheet. It's not a sexist remark.
No, but that's the part you point out about income.
Well, I don't know if she could speak Farsi better.
So I'll cut this short. So the thing is that because the Shapley value is characterized by order independent summability, what's going to happen is that in analyzing these new cost sharing methods, we are not going to have order independence. So in some sense, the order is going to play a big role, and it's going to be like an online problem. We're going to have to sort of consider, we're going to upper bound over different ordering. So that's what makes this summability analysis interesting in some sense. So I would give an example, but I have a little bit to talk about. So I'll come back to this if I have time. So I was going to tell you about Jane Vazirani cost shares for the Steiner tree method, and tell you what it takes to bound summability in this context. Come back. So what we've sort of seen so far is that we've sort of identified optimal Mullen mechanisms for various problems. But it turns out that for certain cost functions, Mullen mechanisms are really bad in the sense that for problems such as vertex cover and set cover, there are really bad lower bounds on both the budget balance and the social cost.
Who's that?
Yeah, that's
I know that. I miss him. I mean the Tom.
Oh, that's Mehta.
Oh, that's Mehta.
Yeah. So, in recent work with Mehta, Rough Garden, we propose slightly different, a slight variation of Mullen mechanisms, which have some nice properties. Even though they sacrifice a little bit of incentive compatibility, they're not group strategy proof. They are still strategy proof. They in fact give you much better efficiency and budget balance bounds for several problems.
So what do you mean slightly there?
So Mullen mechanisms are known to be group strategy proof.
Right. This is
In fact, almost all group strategy proof mechanisms are Mullen mechanisms.
okay.
These acyclic mechanisms are weakly group strategy proof. By that, what we mean is that it is never the case that in a manipulating coalition, all the people gain from the manipulation. So, but it's still strategy proof and that kind of thing. So, and also it turns out that many primary dual algorithms naturally satisfy these conditions required by acyclic mechanisms. So they're kind of easy to design as well. So this is recent work. Thought I'd just say a little bit about this. So the main open question in my mind is that can you have strategy proof mechanisms that give you constant factor approximations of both budget balance and efficiency in terms of social cost. So this is something we don't have a handle on yet. It will probably require new mechanism design ideas.
That's the answer to your first question.
Right.
Do you get it now?
I got it.
Long back.
The only thing I remember in the news that the barber opened his own website to sell because
Her, Or the husband of the
no, the barber.
Oh, because eBay took it off from the...
eBay, there were a lot of fakes and it was against the policy.
Oh,
so
I
what
see.
you have is fake auction most likely.
Yes, I think so. Yeah, because the eBay thing, right?
Yeah.
So I think all the work that we've been doing. So I've been doing with Timber of Garden. What we've sort of realized is that auctions typically involve multiple objectives, and if you see most of classical sort of auction theory, it's full of impossibility results. And it turns out that approximation is a good way of trying to see if you can simultaneously approximate multiple things and figure out the tension between different auction objectives. So recently we had a result in the context of pay-per-click ad auctions in a very simple setting. The setting is that the values per click are drawn IID from a common distribution D, which satisfies the monotone hazard rate condition. So actually it works for a slightly larger class, but let me just say this. So intuitively, it's the class of distributions with tails shorter than the exponential distribution. So the exponential distribution, so the monotone hazard rate is something like this. So it's sort of, so the people who are doing failure analysis use this as a common model. So the idea is that suppose you're discussing the failure of a system, the assumption that if the system has sort of not failed for a while, and you ask, what is the probability that it will fail in the next time instant? This particular number keeps going up as the system has not, as the amount of time increases.
It depends on the history.
Right. So
inversely on the history.
Right. So as you've gone further and further, the probability of instantaneous failure increases.
But failure could also be success.
Yeah, sure. That is true. Very philosophical. So, in some sense, when we define exponential distributions, we essentially assume constant hazard rate. So the lambda in the definition of an exponential is the hazard rate, effectively. So, which is why, if you have a monotone hazard rate, so we can do it with monotone.
So exponential
is included.
is
Yeah, exactly. So actually, we can do some distributions beyond this, but it's a little harder to state. So in a case lot pay-per-click auction, here are the results. So two results. The revenue of the efficient auction with n plus k bidders exceeds the revenue of the optimal auction with n bidders. So what this is saying is that a little bit of added competition for the slots outweighs the benefit of calculating reserve prices. Because the efficient auction is also a very simple auction, it just takes the bids and does something. So it's an argument for simplicity also.
I see. So so exactly. So you're saying don't calculate reserve prices. If you have enough room on the page, just put more slots on the page.
No, actually it means that go and find more bidders.
It's hard to...
Go find more
bidders.
Find more
Yeah.
bidders. Good.
So if you're a...
If you have 5 slots, just find 5 more bidders.
That's
Right,
right.
and you'll do much better.
Yeah.
And
So-
that makes a lot of sense.
So if you're a small advertising company and you had these salespeople, and then you tell them that,
Like MSN, we don't have many bidders, so we we should tell them that we should get more
Get more
customers.
bidders. Yeah.
Which I'm sure they don't know.
Which means you have to hire more salespeople.
No, but this is also a question of what would you do with the salespeople? Would you have them calculate priors for the existing market that they have, or ask them to go and find more bidders? And so this is saying that the second is better.
Right. Which the advertisers knew and which we theorists hoped was not the case.
So hopefully one of the many conditions that I use are not satisfied, so we still have work to do.
So footwork is better than thinking.
Yeah, in this case. So also the efficient auction gives a 1 minus k over an approximation of the optimal revenue.
What's K?
So
Number
these
of slots. Yeah.
So these are a couple of interesting results. We're still working on trying to understand these results completely.
Is there bound in the other direction?
We don't know yet. This is like work I did last month so that I could come and talk about it here.
Okay.
But when K is 1, you're saying that the
Yep.
revenue of the efficient auction with n plus 1 bidders exceeds the revenue of the optimal auction.
So yeah, in particular,
So
let's
for
consider.
single item auctions, I thought there's a classic result that.
So we are in fact using those techniques and building on them. And essentially, I think what we find is that those techniques extend to these kind of auctions as well. Okay.
I have to get going.
Yeah.
Thank you so much. That was really
So
nice.
what if the distribution, what if you know the distribution of these bidders?
Right.
And you actually know that maybe you have two classes, you have a rich and poor class. Some classes are willing to pay a lot more for cancer treatment than the other.
So are we now wondering about the result on the previous slide or the one before?
No, this is the last one.
Oh, the last one. Okay.
So do you need that the distributions are IID or can that be?
So this is exactly what we are thinking about right now. So it turns out that because both set of bidders share the slots and they provide competition for each other, in some sense, adding the bidders which are poor, you need to add more bidders who are poor to have a result like the one in the previous. So
And less rich ones.
yeah. But it's something we're trying to see how to formalize, and that's the. So maybe that's one way of doing it, to have two classes, and yeah, I think that's a.
And if I go back to this example, now if I would draw people from a distribution where is there some way of saying if the tail is large enough, then it may be better to sort than to split?
It's possible. Yeah. In fact, that may be the case. So I think I didn't answer one question, which was about in Moulin mechanisms, can we delete all the players in a particular step? And just to complete that, since we require the cost sharing method to be cross monotonic.
Then if you delete.
Yeah. So if you delete someone, if you don't delete someone now, you can always delete him in the next step, because his bid remains the same and his cost share could only have gone up. So he's still ripe for deletion. Okay, thanks.